trying to prove that we're talking about weights last time. Unfortunately, I didn't bring those papers. You remember the setup? We had a phi, a weight on M, actually M plus on a one-level algebra, and then they were associated to that. We associated these spaces. This the domain, the positive things where this phi took a finite value. This n is something like L2. Those x's, for which x star x is in the domain. And then we defined an m, which can be thought of as n star n, by which I mean the linear span of things of the form x star y, x, y, and n. And we proved some properties about this. For example, that n is a left ideal. And that M is actually a star subalgebra. This I think we had verified last time. And the next assertion that I wanted to prove was that D equals M plus. The positive elements of this M are precisely D. Right? So if you think of phi as an infinite measure, then D is just all those positive functions which are integrable. And this n is L2 intersect L infinity, and this M will be like L1 intersect L infinity. So we're trying to say, okay, so let us see this. So before this we had proved, we had seen that D is a hereditary cone. By that I mean if x and y are there, then x plus y is there, and anything smaller than x is there. Okay, so using that, so I want to first prove that, okay, why is M contained in D? So let us take an element in N. So this looks like some for L equals 1 to n of y star x, where x, y belong to n. And that is what M looks like. Anything in M looks like. y L star XL. Now I want to use that polarization trick. So 4 times Z the sum of 4 times y star. See, y star x is clearly a Hermitian sesquilinear map of m cross m into n. Okay. Consequently, one can apply the polarization identity. What does that mean? That means I can write this as summation j equals 1 to 4, 0 to 3, whichever way you want to. I power j so xy going to y star x is our sesquilinear form, right? So then you take so we looked at xy going to y star x, that is the sesquilinear form. Okay, so what is the thing there? It says you must look at, if you want q of xy, the q of xy is sum of x plus xl plus I to the j yl star xl plus I to the j yl. Right? That was the polarization thing which told you how to decompose a sesquilinear thing, a Hermitian sesquilinear thing. Note that this is Hermitian. Y star x star is the same as the other thing. Okay, but now notice that you prove that n is the left ideal. So x plus iy is in n. So each of these things is in n star n. Right? So this whole linear combination is in M. No, what do I want to say? No, I want to say that, so actually what I should have said was, over here, any element of Z in M implies Z is a linear combination of 4 elements of M, D. Okay. See, this I can write as sum j equals 0 to 3 I to the j. Take the sum over L inside. Then that inside sum is going to be, see, these are all in n star n, and we assume that it is in n star n, that means phi of this is finite. You notice that each of these chaps belongs to D. Because the XLs and YLs are in N, so the sum is also in N, so that star Z has a finite phi value. And so this is positive by construction. Here the positive element with finite phi value. So if I now take the sum inside this, that will prove the statement about everything in M being a a linear combination of 4 elements of D. Correct? So this proves this fact. Okay, so as far as for this assertion, see, D is, by definition, it is contained in M plus. By definition, and it is in M because why? N star N is M. So what do you mean? And so I want to see D is in M because A and D, that means A is positive. Implies A is positive, so A to the half will be in N. That means A star A is in N, so it is in D. So D is certainly contained in M. So for the reverse inclusion, so we go back to this thing. No, we don't have to go back to this. For the reverse, suppose Z is self-adjoint. So Z equals summation YL star XL, and suppose Z is self-adjoint. See, I am trying to prove that D is contained in M. D is contained in M plus is what I want to say. It considers only positive thing. I just have to show that D is contained in M. I don't know. Sorry, that I will show that M is contained in D. Sorry. Okay, so that means I must write this as things in linear combination of things in N star N. But what is this? No, I must show that this belongs to D. So suppose, and I want to show that if Z is positive, I want to see that it belongs to D. This is what I have to prove. I have to prove that M plus is contained in D. So if it is positive, then it's certainly self-adjoint. So I can write, for example, 2Z equals Z plus Z star. which is, let me spell it out, YL star XL plus the adjoint of this. And what is that? That is just XL star YL. Okay. But now I want to observe the following thing. This I want to observe is let me take XL plus YL star XL plus YL. So what will I get? These are the cross terms. Right? Remaining will be XL star XL plus Y star YL. So if I take this and if I take XL minus YL star XL minus YL, if I compare these two, only the cross terms will be negative here and there will be positive here. I want only the cross terms, so if I subtract this, I will get twice the cross terms. Which is certainly less than or equal to some more. If I subtract something positive from something, then that is smaller than this bigger thing.
1 by 2, 1 by 2.
Huh?
1 by 2.
I have 2z outside here, no?
Second line,
How?
1 by 2.
Yeah, 1 by 2. 2 into cross terms. If you subtract, cross term will come twice.
Okay, so let me take 4z equals twice z plus z star. Now, who are the XLs and YLs are in N. And N is the left ideal, so it is a vector space, so the sum is also an N. So this whole thing is in N star N. So this whole thing, see, there are a bunch of positive things. Each of them is in D. Right? Why? What did XLs were in N. That means what? And YL is in N. So XL plus YL is in N. That means that star that has finite phi value. That means that star that belongs to D. So this finite sum is again in D. And that because of the hereditary property, Z must also belong to D. Therefore, we prove that M plus contained in D. So D equals M plus. Very good. Now let's put all this to use. I want to show you the first non-trivial example of a weight which should by rights have been covered in the first lecture itself. So example. I take M equals B of H. So notice that if you take a positive element, see, elements of M can be represented by matrices. H is always for us separable, so they are represented by countable matrices. And if I start with something which is positive, then all the diagonal entries will be positive. Because the diagonal entry, if it's the base, if we write, express a positive operator with respect to the orthonormal basis xi n, then the diagonal entries are x xi n, xi n. So those are positive, right? So I want to observe that x xi n summation x xi n xi n so x in M plus implies this is independent of the basis. I'm talking about an infinite sum, but it's an infinite sum of positive things. Now this sum is by definition something in zero infinity. Right? That means what I should show is that if it is finite in any one basis, then in every basis it is finite and the two sums are the same. Okay? So proof, suppose summation x xi n xi n finite for some for an orthonormal basis. So let's take any other orthonormal basis. Let eta m be any other orthonormal basis. Then, okay, I'm going to do some fudging. So, look at this series. Sum over n x xi n xi n. So this I want to write as use the fact that the etas form a basis and you'll get this. Okay. So then I want to say this is the same as of this. So why can I say this? So I'm interchanging the order of summation
positive.
Well, no, xi n eta n. So if I know, if I put the modulus and if I know that the double sum is convergent, then I can use Fubini's theorem. If you put the double sum, what you know is that each of these sequences separately, if you look at it as a sequence in M, let me look at the sequence, doesn't matter, look at the sequence in N. So I want to say, if you look at this is an L2 sequence. It is the Fourier coefficients of x I n with respect to eta m. So I fix an n. So for as m varies, there is an L2 sequence, and so I want to say sum over n, sum over m. Right? I am applying Cauchy-Schwarz in little l2. The sum of the squares of this is the norm squared of x I n, and for this will be the norm squared of xi n. Right? So this is finite. So I can sum in any order that I want. And I want to get it in that form. So let me write this as eta m xi n. I'm writing the second term first. And this I'll write as xi n x eta m. X is self-adjoint. We've written them in the opposite order. I've just taken the x over to the other side. But what does this give me? This gives me sum over m. Eta m x eta m. And there is the same as sum over m. X is self-adjoint. I can bring it back over to the same. So if the sum is finite in one basis, it is finite in every basis and the sum is the same. Right? So you see a neat proof of what we spent the 2 or 3 days to do for. So I define trace of x for x positive. I define this to be summation x I n xi n. So I've defined something for positive elements which take values in 0 infinity. It is clearly additive and it is clearly you can pull out positive constants. Right? So it satisfies the first requirement for a weight, namely the trace of ax plus y, alpha x plus y equal alpha trace x plus trace y for alpha positive x, y and m plus. So I've defined the weight on B of H. And what has this said? This has said, what is your D? D is just all those positive x with finite trace. These are the things for which the trace makes sense. Okay. This is the D for trace. And what is N? Y is some x star x. Y is x, sorry, y star y is in D. So what does that mean? That is equal to saying that for every orthonormal basis that sum must be convergent. Right? If you not leave summation y star y is in is finite. I can take the y over to the other side. So I find norm of y is in square finite. And this is for all orthonormal bases. In and the value, this whole value is in, which is just trace of y star y, is independent of n, the orthonormal basis n. Okay, and I want to say, okay. So I want to just observe one. See, all this is just using the general machinery for weights that we did before. But there is something that holds here which is little more than what holds in usual. See, usually what you know is that n is the left ideal, n star is the right ideal, and n star n will be just a star subalgebra. It will be contained inside n intersect n star. But I want to say that see, a consequence of this being independent of this orthonormal basis is that no, not correct. See, separately, I want to observe that summation norm y is in squared by doing the same kind of trickery that I did before, but you have to be careful with showing that something is absolutely convergent. Double sum is absolutely convergent and you can interchange the order. So by taking a different orthonormal basis, So if I write this as summation over n m mod y n eta m squared. And that's what this is. Sum over n norm y n squared, sum over n and m of this square of the Fourier coefficient. Now, by the same kind of thing that I did before, the double sum will be convergent by Cauchy-Schwarz like before. And so if you write it the other way, if you sum over m and n, you take sum over m and then you take this y star here to the other side. And because you have an absolute value, you can think of this as sum over m y star eta m by n square. The absolute value doesn't change in the complex conjugate. That means you've shown that okay, so a little terminology. So one called such a y, elements of n are called or n is the so-called class of Hilbert-Schmidt operators. One calls an operator Hilbert-Schmidt if it has this property. The trace of y star y will be finite. That is the same as saying that sum of norm y n squared is finite for all n.
So what about sum with n last one? Where sum over n goes?
So sum over m of no, I wrote the wrong thing. No, this is still mn, but now you can write this as sum over m norm of y star eta m squared. So what this has shown is that if y is Hilbert-Schmidt, then y star is also Hilbert-Schmidt. That means this shows that in this case, n equals n star. To say that it is in n means it's Hilbert-Schmidt. And you've shown that if y is Hilbert-Schmidt, so is y star. But you know that n is a left ideal. So in this case, n is actually an ideal. Right? So there's some names for this. So one says, so n is an ideal. Is an ideal in B of H. So I will use the notation. In this case, n trace. So a notation or definition / notation. This n trace is I'll denote by C2 the class of Hilbert-Smith operators. Okay. And what is M trace? This is finite combination of the things from n star n. You take a product of two Hilbert-Smiths and add them up. So one calls this C1. This is called the class, the trace class. Operators. So I want to digress a little bit with these trace class operators, or even about Hilbert-Smith operator. See, notice that which is bigger, C1 or C2? This is n star n, and n was an ideal. So m is contained in n. And because n and n star are the same, so there's just you're really looking at C2 squared is C1. By squared I mean C2 times C2. Okay. One of the simplest way to do it. Now C1 is an ideal. We've shown, we know that C1 is an ideal. That means X in C1. Huh?
C2 ideal.
C2 is an ideal, but I'm saying C1 is also an ideal. So C2 an ideal, this plus C2 ideal in M implies C1 is an ideal in M. I take XY X in N. If I take anything in N, hit it on the left or right by anything, I'll stay in N. So if I take N times N, if N is an ideal, then N squared is also an ideal. Right? Because if you multiply, it doesn't matter, you get the same thing. Okay. Now if you have, whenever you have an ideal in a one-dimensional algebra, if you take something in M with polar decomposition X, U mod X, then it is true that U star X is mod X. Right, because U star U, if you recall by the definition of polar decomposition, U star U has initial space at the support of mod X. So U star U is identity on the range of mod X. So this means that both X and mod X are multiples of one another. So if you take any ideal, x will belong to that ideal if and only mod x belongs to that ideal. And x in C1 or C2 is at j equal to 1, 2. If and only if mod x is in Cj. Okay, so I want to I don't know any other way of saying this, then we will do this way. Like this. Okay, we haven't spoken about this at all, but this must be spoken about in any course on operators, so I'll just digress a little more now. Suppose you take something in either of these classes, the Hilbert-Schmidt or the trace class. Then, see for example, suppose you take an x in C2. We know that is equivalent to the mod x being in C2. Okay, but see this means that norm of summation norm mod x n square finite rod orthonormal basis n. Okay, so I want to say from this that I want to conclude that see mod x is a positive operator, so one can do functional calculus too. So I want to say if I take any see this makes sense. This is the indicator function, which is 1 after epsilon and 0 before that. This function of mod x is going to be a projection in that one-dimensional algebra generated by mod x. So I want to say this is finite range. This is a finite range projection for all positive epsilon, strictly positive. See, what property does this thing have? See, look at the function indicated epsilon infinity. This function of t on the real line.
What is this
it's a projection of finite rank. That means the range is finite dimensional. It's a projection whose range is finite dimensional. Usually for a matrix, if you have a projection which is a matrix, which is finite dimensional, and if P is a projection in the matrix algebra, its rank as a matrix is the same as the number of independent things or whatever. That is the same as the dimension of the range. It's the same as the trace. If you take this what we define as the trace to some of the diagonal values, if you take the trace of a projection, okay, I'm getting ahead of myself. I haven't proved these properties. Okay, so let me prove. See, as a function of t. See, this is is 1 after epsilon, 0 here. This is what this looks like. So if I take t times indicator epsilon, that looks like the function f of t equals t but chopped down to epsilon infinity. So this is epsilon. See, f of t equals t looks like this. You just cut it down in the first part. So this is the function which is 0 before epsilon. After epsilon it is t. That means that this is bigger than or equal to see the smallest value, so I want to observe this bigger than or equal to epsilon times indicator epsilon infinity. Right? On epsilon to infinity, t is greater than or equal to epsilon. That's what I'm saying in a fancy way. But if I state it in terms of functions, if I now apply the functional calculus is a star homomorphism. So such mappings preserve order. So it will be true that mod x times indicator of epsilon infinity, mod x be greater than or equal to epsilon they're getting very complicated. Let me just call this p epsilon for the moment. See what does this say? This says that if I take, suppose xi1, xk are orthonormal in a range of p epsilon. I want to see what this thing says. Then this says that summation I equals 1 to k. I want to take this xi. But p epsilon xi is equal to xi. Mod x p epsilon xi greater than or equal to epsilon times summation P epsilon psi I psi I. And I have taken vectors in the range of P epsilon. So P epsilon psi I equal to psi I for every I. That means I can forget about this, I can ignore this P epsilon. So what does this say? This says that and what do you know about mod x?
We start from square root of mod x.
Yeah, so started with square root mod x. Okay, see this is the same as where mod x is bigger than epsilon means the square root of mod x is bigger than square root epsilon. And this is the same as indicator of root epsilon infinity. No. Of mod x power half. I wanted, okay. The expression, okay. And so I want to say the same thing with mod x power half. Root epsilon mod x power half mod x power half. I don't know what no. Sorry, you confused me. I was going along the right lines. So now let me stay with what I had said before. Sorry about this. So what does this say? This I can write as summation mod x to the half psi I squared greater than equal to k root epsilon.
Why root epsilon?
No root epsilon, only epsilon, sorry, k epsilon. Okay, so going back, see mod x power half is where? Mod x
Mod x C1. X start from C1. X start from C1.
Okay, but even if I start with C2, I will get this, okay.
C1. Then square root in C2.
Then mod x power half
In C2.
is in C2. And means summation mod x to the half by n squared is finite. Okay, so what is all this said? If I take any k orthonormal vectors in the range of 1 epsilon infinity of mod x, then k epsilon, okay, so see one uses one notation. See, for a Hilbert-Schmidt operator is by definition somebody for which this quantity is finite. So let's call it the Hilbert-Schmidt norm. Norm of mod x to the half. I call it Hilbert-Schmidt. I define the Hilbert-Schmidt norm by actually the square. The square. Only the square will be a norm. Okay, so to try and salvage what I've made a mess of. So what I've tried to show is that if I take the indicator from function of from anything positive to infinity for mod x, see this see what is this? This is, therefore the Hilbert-Schmidt norm of mod x to the half squared. So what is the Hilbert-Schmidt norm of mod x to the half? It is the sum of that xi n squared for an orthonormal basis. Here I just had some orthonormal set. I extend that orthonormal set to an orthonormal basis any way I want. Then this sum is going to be smaller than or equal to the sum of the entire infinite thing, which is the Hilbert-Schmidt norm. Right? So this is so this is going to be greater than or equal to summation 1 to k of norm of mod x to the half xi I square. Which is greater than or equal to k epsilon. So if you fix epsilon, the whole point behind the messy inequality is the following thing. If you fix epsilon positive, then k must be less than or equal to dimension of range of p epsilon k epsilon must be smaller than this by epsilon. So whatever the dimension is, I can find that many eigenvectors, orthonormal vectors in that space. Okay. So this says that this cannot have more than
k is less, will equal to dimension of n.
sorry?
K equal to wave dimension of range of this projection.
K is what?
K may be equal to this one, dimension, range,
Divided by epsilon, that number is somewhere, not even be an integer. No, but whatever it is, I'm saying this is finite. For every epsilon, we've shown that the range of p epsilon is finite dimension. So what have we shown? We've shown that if you take if x is a trace class operator, we've shown that dimension range 1 epsilon infinity of mod x is finite for all epsilon positive.
square
Huh?
range of square.
Dimension of this is fine.
No, but this is what we're taking there. The no. Because when this quadratic, this polynomial, Pascaline form, you want to change it to quadratic form, that is why we took the square root and so on. Anyway, it doesn't matter, but since you're saying for all epsilon, the thing, or its square root is the same thing. So each of these things has finite dimension. Now these projections are all in the one-arm algebra generated by mod x. So they will commute with mod x. Then T and indicator of some set as functions they commute. If you apply the function of calculus, then x and that indicator of x will commute. That means mod x is a positive operator which leaves this finite dimensional space invariant for every epsilon. Now if you think of what that says, so suppose you rather than epsilon, let me say 1 by n. Yes, I just want some countable thing finally going down to 0. Now each of these is finite dimensional. Maybe this, let me suppose this dimension is let's say k1 plus kn. I'm writing this funny thing because I want to take indicator, see there is 1 to infinity. This fellow has the range of this projection is k1. And then from half is 1. So then from half, this whole thing has dimension k1 plus k2. So k2 is really this space. k2 is the dimension of this space. And then I take 1/3. And then here I have to mention K3. That means K3 will be the dimension of range of 1 by 3 to half of models. And if you take this is an increasing family of projections. 1 by n to infinity of mod x, they are an increasing family of projections, and they will converge to they will increase to the support of models. It's the same thing. If there is indicator of open interval, because it is the same as 0 infinity. Okay, so what has one obtained by all this? If you look at this positive trace class operator mod x, then the whole Hilbert space, I don't know, it is a positive operator. See, 1 is equal to indicate. See, the spectrum of mod x is positive. So this I can write as indicator 0 plus indicator 0 infinity of mod x. This I can write as indicator 0 plus this summation indicator 1 by n to 1 by n minus 1. I just take all these little intervals and I add them all up, then I get a union to exhaust the entire positive line, and I transport that by the functional calculus to get an orthogonal decomposition of the Hilbert space into this one space, what is indicator 0 of mod x? Indicator singleton 0 of mod x is the projection onto the kernel of mod x. So the entire Hilbert space breaks up as some H0 direct sum over all n equals 1 to infinity Hn, where all these Hns are finite dimensional. Actually, dimension equal to Kn by Mi in notation. This is Kn dimensional, and all these subspaces are left invariant by the positive operator mod x. If you have a positive operator on a finite dimensional space, then you have your spectral theorem available to you. What does it say? It says that you can diagonalize. There is an orthonormal basis for Hn with respect to which mod x will be diagonalizable there. So on each of these spaces, each of the pieces you will choose one orthonormal basis, You put them all together. So what this will say is that this mod x is actually will look like possibly a big fat zero. That 8-0 might be infinite dimensional. We don't know anything about 8-0. But the others are a bunch of finite dimensional spaces. In each of these there is going to be a diagram. So that is if you remove all these lines here, on the complement of the zero piece it is already given by diagonal matrix.
Mod x, any x belongs to h.
Huh?
H can be written as direct sum of h naught plus or finite dimension.
But-
Any h.
Any h.
Means h Hilbert space can be written as h0 plus h1.
What is the any statement? Any is for what?
So what is the direct sum I have not written?
It is this direction. See, indicators, see the entire positive line. See, the spectrum of mod x is in the positive line. So I spread it out, take away singleton 0. Other than that, take everything from 1. That range will be h1. And take everything from half. That between half and 1 that will be h2. Between 1/3 and half that will be h3. By that I mean the indicator of that interval of mod x will be those h's. So the Hilbert space has been written as a direct sum of subspaces, each of which is left invariant by mod x. And in fact, if you look at the eigenvalues of mod x on the nth piece, the function t between 1 by n and 1 by n minus 1 will take values between 1 by n and 1 by n minus 1. That means all the eigenvalues in Hn will be between 1 by n and 1 by n minus 1. Well, I'm just saying that see the spectrum of mod x restricted to indicator 0, 1 by n to 1 by n minus 1 of mod x, the range of this. If we take this spectrum, that will be contained in 1 by n to 1 by n minus 1. And that means it's a finite dimensional space. The spectrum is sitting there means you can diagonalize it, and the eigenvalues will all be in this range. So what this says is that if you look at this picture I draw, from 1 to infinity, above 1 there are only finitely many eigenvalues. In fact, above any epsilon there are only finitely many eigenvalues. Then you will find an orthonormal basis by piecing these together, so that here the eigenvalues are all bigger than 1, here they are all between half and 1, blah blah blah. So what we've seen is that this mod x is an operator which is why did I want to say all this? So the conclusion of all this is that mod x is diagonalizable. It means you can write diagonal in some orthonormal basis. It looks like this. Direct sum a 0 on H0. I don't have any control over the size of H0. So the countable sequence of eigenvalues which decrease to 0, and this could be finite also. If mod x had finite rank, already at some stage you have caught everything. Only if the spectrum goes all the way down to 0, it will be true that each of these h's will be non-zero. Or infinitely many of them will be non-zero. So, for you to say it is a sequence converging to 0, to say it is a sequence, it must be infinitely many. It is either finite in number or it is a sequence converging to 0. And this is a feature of all these so-called compact operators, and so this says that if we take any positive operator in this, it has this property. But the reason I wanted to say all that was to get some conclusions that I wanted to read off.
Decreasing to 0. We
In
have
the-
Lagrange and 0.
In the nth block, the eigenvalues are between 1 by n and 1 by n minus 1. So, if either there are only finitely many lambdas, in which case they have nothing to say. But if infinitely of the blocks are non-trivial, then you will have infinitely many lambdas which will necessarily decrease to 0. Okay, now the reason I want to say, said all of this is that so what I've proved is that if I have let me call it more, if I take a row in C1 plus, then I was calling it mod x before, but suppose I start with something that is already positive. Then we've shown that in a suitable basis with respect to some basis, rho looks like diagonal lambda 1, lambda 2, blah blah. See, I can take care of the zero pieces. See, if you write like this, then you'll have to worry about what you do with the zeros, where do you put them in. So if there are infinitely many zeros, then you interlace those, you put them in between these lambdas. Of the only finitely many of them, you just put them somewhere, anywhere, I don't care. So if it is a positive trace class operator, it can be diagonalized. There is a motto with lambda j is non-negative and this trace class. So if a positive trace class is operator, that means the sum of the lambdas is finite. So conclusion is that if I take any okay, okay, and suppose x is anything now. Take any operator x. Then we have seen that the trace class operators form an ideal. Right? That means in fact, I'm during this, so I guess if you have said this properly. No, we're running out of time. See, it is actually. Okay, so see on this, okay. See on this, what we call M, everything in M is a linear combination of four things in D. And for things in D, we show that no matter what orthonormal basis you choose, the diagonal is going to be summable. The value of the sum is independent of what basis you choose. If you take anything in M, you can take it as a combination of four things in D. So that means anything in M also will have the property that the sum of the diagonal entries will converge, will be absolutely convergent for any orthonormal basis you choose, and it will be independent of what basis you choose. So for any row in x and psi in M implies trace psi equal to summation psi n n. That is the sum of the diagonal entries in any orthonormal basis, and it doesn't matter which basis you choose, because we proved the thing for positives, and everything in M is a linear combination of four things in the positive things. Okay, now the reason I want to say all this is that this will tell me that if we take an x and I have tried to ensure that you are expert in multiplying things by diagonal matrices. If you take x times rho, it will have diagonal entries. What will the diagonal entries of x times rho be? What will the ij entry of x row be? X is the matrix xij. So if this is xij, what is x row? Row is the diagonal matrix on the right side. So taking this
First row of x will come in the.
I have told you again and again, you take a diagonal matrix alpha I, multiply by a fat matrix, multiply by another diagonal matrix, beta j. The answer will be the matrix alpha I, xij, beta j. So please don't tell me all these stories in the future. Tell me the answer precisely. So x row is going to be a matrix xij lambda j. And you know that the trace class operator from an ideal. So x row is also a trace class. So its trace will be the sum of its diagonal entries. So what is trace of x row? Summation over j xjj lambda j. And what is trace of rho x? Now rho is sitting on the left side. Okay, so at least which I'll stop at a place I'll be happy with. We proved that this holds for all x and m rho in C1 plus. But what is special about C1 plus? Any self-adjoint in C1 is expressible as a difference of two things in C1 plus. And anything in C1, if you look at the Cartesian decomposition, can be written as a linear combination of four things in C1 plus. With the same thing that we did before, M and D, they're coming again and again. So everything in C1 is a linear combination of four such rows. So for each of them this thing will hold, so it will be true even without achieving any positivity. So, okay, I've already gone 10 minutes overboard, so next time we'll reap the benefits of this. I'll try to connect up with the pre-dual of B of H and so on next time.